Okay, so as I was saying, this title of this course is called Making R Easier with Tidyverse. And so what we've covered so far is the basics of interacting with R, building variables, then starting to actually process or do things to the data that you have in R. These different data types, you can then apply functions to them. And quickly you can see how you can string all these things together and start to build like quite complicated operations with custom functions to create plots and outputs for your analyses. And this is really great, but there are, to kind of smooth things over and to make things easier for you, there are some tools that we can teach you from this world called Tidyverse, which should make life easier for you. And so when you think about data, we often face very similar problems. Every single data set that you get is quite different. Sometimes it's very, very, very different. And so having a uniform set of tools to deal with that is quite tough. It's also, as we were talking about yesterday, I think we had an example where we were setting the limits of plots using min, max, and range. And there were we came up with about 3 or 4 different ways to do things. Which really comes down to this idea that encoding is a problem solving. Most of what you're doing is problem solving. And every single problem has many, many solutions. There is often the most efficient, but there are several alternatives, and they can all have their own benefits and costs. And a lot of that benefit and cost comes down to the user experience and what are you comfortable with? What are you familiar with? And so we all have this kind of favorite syntax. And so many of the things that you'll need to do to your data exists in base R. We've covered that over the previous couple of days. But the issue is that they can be quite inconsistent. If you remember with the plotting, there's all kinds of different parameters that you have to put in depending on what kind of plots you have. And even though it seems like you're giving it the same, like the argument should be the same between, say, a bar plot or a box plot and a regular plot, the arguments might have slightly different names. And so that can make it a little confusing because then it's hard for you to store all this information in your head, right? And so this gets even more complicated when you're dealing with data frames that are not standardized, they're not the same each time. You're getting all these different inputs and then you want to create something similar as an output. So what often is the result is you have this code that's quite confusing. You have to do quite a lot. You make stuff that looks kind of hacky. And that's a kind of, I guess, a jargony term because it's hard to know what code looks hacky when you don't have as much experience. But it's code that basically doesn't flow. You can't read the story of what the code is trying to do in a very intuitive way. And a common example of that is nested functions, where you have one function and then you have another function around that, and then you have another function around that. And so then trying to figure out the step-by-step of what the code is doing is really tough because you have these kind of functions built on each other like Russian dolls. And so Tidyverse came in at this point and is trying to create a system to help rationalize and normalize some of these processes. It sounds a bit cheesy, but it's a philosophy of how to deal with data and data analysis. And using some of these ideas, it can actually make your life a lot easier. And so the Tidyverse is a community with a shared philosophy about how to do things. And they describe themselves as an opinionated group of packages. And by that, they mean they have ways that they want things to be done. And as a result, because of this uniformity and this opinion that is shared, the packages talk to each other quite easily. And it's similar to the community of Bioconductor, which will, for those of you who are joining us next week, they're opinionated in a slightly different way, but there's quite a lot of overlap between the communities. And so what the main ideals behind it is you should have more efficient code. It's easier to remember the syntax and it's easier to read the syntax. Okay, so not only is it easier for you to write it, but it's easier for you to understand it when someone else has given you some code to look at. And they have a whole a manifesto here, which you can click. It's literally a manifesto. And so you can get an idea of what they're all about here. And so that was kind of like the hand wavy aspect of what it is to be tidy, but what does that actually mean? It's a very defined coding style. It's a defined style for data formats. It's a defined idea of what packages should look like. And then a big part of when you have a community like this and they're all pushing in the same direction, if you have this kind of unification of where they think R should go. And so that means they can actually influence how the R community evolves, right? Because it is a community of mostly open source developers. And so they can actually have a say because they're contributing into the way that R evolves itself, especially when the head or the main person behind Tidyverse, Hadley Wickham, is head of RStudio. So that kind of underlines, I think, why these are important skills to learn. Not only is it going to be useful for you, this is going to be probably the way that R is slowly moving towards. And so picking them up early will be useful in the long run. So there are a lot of packages that are Tidyverse packages, but the people behind Tidyverse have a core set which they actively maintain and they see as the backbone of the Tidyverse. And so ggplot2 is the one we were talking about yesterday, so we won't really talk about that very much. We have readr, that's for reading data in. dplyr, that's for actually manipulating the data. Tibble and tidyr, this is for, there's a specialist kind of data frame called a tibble, which we'll talk about. And the tibble package works with these tibbles, and tidyr is a kind of a partner package that helps you actually tidy the data. Per is almost equivalent to apply in base, and it allows you to iterate over the data. String R is for working with strings, and forcats is for working with factors. And as I said, there's tons of other tools. This community does overlap quite a lot with Bioconductor. So when we get into Bioconductor, you'll find that some of these packages are tidy packages as well. But yeah, like these are really the core packages. And I want to underline something here, that this is the way we've learned how to do things with base R, and what we're learning now are not mutually exclusive. They're really useful tools that you can use in tandem. So everything you've learned so far is not frivolous and wasted. It's really what we learned so far is the baseline, and this is going to be an extra set of tools in your arsenal to make you even better, to make you even better. Okay.
Or betterer.
Betterer, yeah. And so what we're going to do is touch on like the core utilities of some of these packages and their most useful functions. Okay, so there's all of these packages have a lot in them, and so we won't cover everything these packages can do. I'm just put together some of the things that I think are the most useful. And what we won't be covering is per or for cats. But you can look at the longer workshop that we have on our homepage, and there's a link here, because that has some more information about how those work. But I just haven't included them because I don't use them as much. Okay, so the first thing we're going to do is we're going to load in some data. And so if you remember, I haven't actually got the guide here, but if you're joining us for the first time today, or if you've forgotten from yesterday, you can download the data. You will need to then navigate yourself into the R course directory. And that's R_course. And you'll be setting that as your working directory. And then all of the paths that we use today should work. So there'll be, yeah. Okay, and so once you're there within the data folder, there is an R data object which can be loaded in with this line of code. And so inside this inside this data object are several data frames. We have df1, df2, and then two df3s, df3a and df3b. Okay, and you can see they contain pretty much the same information. They're just organized in slightly different ways. So this is some ecology data. It's about fish. And you can see they've done some observations of individual fish. And they've classed them into their age. And they have some length information and some IGF information. And so here it's the same information, but it's split. The variables are split along into one column, or joined into one column. And here the variables are split between two data frames. So when we talk about what a tidy data set is and how to make a data set uniform, there's three things that have to be considered. And this is when we do things in a tidy way, we first start by cleaning our data and we try and make it fit these categories, okay? And so each variable has to have its own column, each observation has its own row, and each value has its own cell, okay? And so when you satisfy these three different things, then you can consider your data frame to be tidy, okay? And so the whole idea of getting a tidy data frame, right, is so that you have an equal starting point from which to use with tools and packages and functions. Okay, so I'm going to chuck up a poll now to see what people think is potentially the which of the data frames is tidy. Okay, and for those of you who haven't got them up in front of them, I can flick backwards and forwards. Okay, so we have df1, df2, and df3. Okay, so I'll remind you of the rules. Each variable has its own column, each observation has its own row, and each value has its own cell. So in df1, okay, and that's what df3 looks like. So I'll give you another 30 seconds to answer. But just to remind you the rules, each variable has its own cell or own column, each observation has its own row, and each value has its own cell. Okay, I'm gonna end the poll in 10 seconds, just in case anyone else wants to join. It seems that we have a tie. Okay. So we have a tie between first and third. Okay, so if we have a look at it, rightfully you've ruled out number 2 because each variable is not in its own column. Okay, so you can see how it's not df2. And in df3, really, although it matches the criteria, each observation is its own row, it is in separate data frames, so it is more complicated. So I didn't add that part in the description, but in reality, this is not super useful to work with because the information is spread out. I think it goes into this idea that each observation has its own row. Really, each observation can't have its own row to the point of being in a different data frame. Okay, and so 1 satisfies all these criteria. We have each observation, so this would be basically each fish they found, the information associated with it. So we have the variable for common name, the variable for age, the variable for length, and the variable for IGF.
Can I ask a question about this?
Yeah.
I seem to remember from maybe it was the first day, you showed an example where you substituted the essentially the column number at the far left for, let's say, in that case, it was the identifiers of the genes in the list, so that you don't have to refer to, I don't know, cell 1 or matrix position 1, 2, but instead you refer to the, let's say, the gene name in that working example, if I'm remembering correctly.
Yeah, yeah.
So I'm wondering if like salmon ID follows the same logic, and whether it's considered whatever tidy practice to rather use the serialization of the entry IDs than row numbers or something to this effect.
Yeah, this is actually a really good question. So one thing that is considered when you have a tidy data frame is you don't want to use row names. Okay, you consider a salmon ID to essentially be its own variable. Because it is, even though it's something you're iterating over and you're creating it yourself, it is in itself almost an observation, or a part of the observation. And later on, you may find you want the salmon ID to be available to some of the tools that you use. Say that you're interested in every salmon that is you collected in a certain range of numbers or something like that. So that is a really good question, and they do have an opinion about this.
Okay. And the opinion is leave the numbers.
And the opinion is, avoid using row names where possible.
Got it.
Yeah.
Thank you.
Okay, so we have a question, a comment or a question from John Nicholas. Not sure if it matters, but my head df1 result doesn't have the first line. Oh, I see what you mean. I see. So right here, it doesn't have the fact that it's a tibble.
It also doesn't appear to have what you have in the arrow brackets, right? So
yeah,
right?
Yeah.
Just listening. I don't know.
So so what you're seeing there is it's being read in as a regular data frame. And so what we might need to do is get you to do library tidyverse. But we'll do that also in a little bit. This is starting to show you some of the features of a tibble. Okay, and we're going to get into tibbles very shortly. But that is the difference between a tibble and a data frame. At least visually, you will not get this part and you will not get this part here. But I'll explain what they're doing and the special parts about a tibble. Okay. So, our first data frame is tidy. And so a question I've got in the past about this is why even bother? It's like it's sometimes a lot of work to make our data and coerce it to be a specific format. And really the idea is that if you have a consistent layout, it means it's much easier to reuse code. The tools you use will become a lot easier to re-implement if your data looks exactly the same each time or very similar. It's also R is built on using vectors, and so this way actually will enable you to work with vectors in a much more efficient way. Yeah. So Nathaniel has a question. So df2 is not tidy, but it is in a tibble. Okay, so how is that possible, even though it's not tidy? So a tibble is just a data type. Okay, so a tibble can have anything in it, and it's not that smart. It's a container. It's basically a modified data frame. And so it has a lot of the same rules as a data frame. The tidy aspect is more of like an ethos or a philosophy. Okay, and so these are good guidelines or rules to try and follow to make your life easier later on. However, they're not hard and fast rules, and they're not the only ways of doing things, and are at this point, if it's not perfectly tidy, will not get too upset. Okay, so really the idea behind this, like I said, is with these 2 points, is it enables you to be very precise because it's very clear about the relationship between the data, the variables to the observations, and it's very fast because you're using R at its best. So reading and tibbles. So first we'll load in the Tidyverse. We can do library Tidyverse to do that. Okay. You can also load in the packages you're going to use individually. So you could just do library ggplot2 or library tibble. But if you do library Tidyverse, it gets all of them, the main ones at once. So I like doing this just because I often use several. Okay, and it has this nice extra information. This is something you'll see with Tidyverse. It tells you more information when it installs packages or when it loads packages about how the loading went. This is common to all tidy packages. Okay, so we'll start with reading data in, and so that's going to be read R. And so the way read R works is much the same way as when we saw with read.csv or read.table. But the common feature you'll see with a lot of tidy packages, the way they kind of differentiate themselves in their names and in their functions is they'll use underscores instead of points or full stops. And so they have read underscore CSV. And then they have a variety of other ones. So you can have read underscore table, read TSV, read delim. So a lot of these exist in base. And they work in much the same way. So here we're using the base method to read in this RNA-seq count data. Okay, and so read.csv is the base way of doing it. And if we look at the output, it looks like this, right? It's our data. We have some data. We have some entree IDs for the genes, and then we have some counts. Now, if we do read underscore CSV, it actually starts to tell you things about your data when it's reading it in, and it becomes more, I'd say, user-friendly. Okay, so one of the big things that it mentioned in the manifesto of the Tidyverse is it's trying to make the data much more readable to humans, and everything is about making everything much more interactive for you as the user. And so here we're doing read underscore CSV. It's reading in the same information, and it tells you some extra information about the what it's read in. First, it will tell you, we have these columns that we've read in, and it will tell you what type is used for them. Okay, and so it's interpreted these as doubles, okay, which basically means it's a number. Okay, so doubles are, if you're not familiar with the nomenclature, doubles quite often used in programming to signify it's basically a numeric that you've read in. And so this is the column specification. So this tells you about the column information that it read in. And then you have the actual tibble itself down here. And in the header of the tibble, it will tell you the dimensions, which is nice. So it's 100 rows, 5 columns. And then it reinforces what data type each column is here. So this, I find, saves you a lot of work because you can just look at the data tibble that you've made, and it actually tells you information about the tibble without you having to use another function to be able to actually do it. You can actually also easily control how you read the data types in as well. And so in much the same way as you saw it printed out, if you use the col types argument, you can then say, I have these cols. And you provide the name of the column and what kind of argument it is. So in this case, we know that the entree IDs are a character. And then we also know that all the counts will be integers. Okay. I got a question from John LaCava. It says, I got some Tidyverse conflicts. Is that an issue? Okay, so you always get a few conflicts. So here I have a ton of conflicts.
I see. Cool. I was like, wait, what?
And so what this basically means is that there are two functions with the same name. And so if you try to use, for example, collapse, it's going to instead pick the one that you just loaded in most recently. So it will pick dplyr collapse. Okay, and if you wanted to use iArranger's collapse, it wouldn't be available to you in your environment.
Is there any, control for masking potentially core functions?
Yeah. So generally it's good, like most people who are building packages will not create something that's like called a function called mean or something like that. And so that's a general rule. You'll see most packages will not mask something that you're using regularly. However, there is one that's really annoying is filter which is a dplyr package, masks something that's quite commonly used in annotation DBI, which is something as we get into the more bioinformatics aspects of analysis, you will use quite a lot. And so the way you kind of get around it is instead of just saying, I want to use the collapse function, you just use the full name. So you say the package, you do a double colon, and then you say the name of the function. And that will basically point directly at which package and which function you want to use, rather than it being confused whether you want to use dplyr or iArrangers for collapse.
So you can still use both functions, but you need to specify the package with the double colon first.
Exactly. So the one in your environment is only going to be the one that you loaded in most recently. Yeah. And then to get to the older ones, you're going to have to be more explicit with what you want.
Got it.
But it's always available. It's never disappeared. Okay, so yeah, as we're reading in, you can very easily control the types. So here, it does its best job. Everything looks like a number, and most of the time people just want a number. So it will do double, but here we just easily control, actually I want characters and integers. And it will coerce it to that. And then you can see the data type updated here in the header. So how do these tables work? So they, like I said, they are pretty much like data frames, but they have these extra aspects to them. They are much more column, or the data frames are quite column oriented. To begin with, you know there were specific column functionality for data frames, right? Because you can use the $ to access columns out. Tables are one step more than that. And so in this case, if you just take your table, this is our table. And if you just index it, right, even though it's a 2D array, and typically when you have, say, a data frame, right, if you just ask for the first index in that, it's not possible unless you have a comma to specify both the X and Y axis. Here, it will go, assume you want the column. Okay, and when you do this, it will return to you a new table, and this table will contain just that first column. Okay. However, sometimes you might want to turn that first column back into a vector. And so you can actually use the double brackets here. So double brackets are not just for lists. You can use them on tables. And again, if you supply it with the number 1, it will return the entire first column. But now we're grabbing out the whole of the first column, and it's no longer a table anymore. It's being turned into a vector. So we're really extracting the information and stripping away any other data type associated with it. But you can still use the $. Okay, so it has this kind of interesting merge of nomenclature that's somewhere in between a list and a data frame. So you can use this $, and you'll get back a vector again. Okay, so you can see we have these 3 methods of extracting column information. And depending on which you use, you'll get a different product back. So you can either get a table back, or you can get a vector back. Coercion works in a very similar way to base. So there is an as_tibble function. And this is the data frame I read in the beginning using read.csv. So I did the base way of reading it in. And when I do as_tibble, it's converted it into a tibble. Okay. And as you can see, it's actually made some slightly different assumptions here about what's in each, what are the data types. But you can make also similar updates to the data types following a coercion. And so you can see that here. And so you can do it during the as_tibble process, but you can also update any data type at any time in a tibble using a function called mutate_at. And so what we'll do is we take our tibble. We say we want to focus on the variable that is entree, and we want to turn it into a character. Okay, and this is, I guess, your first taste of like a function in Tidyverse. And really, this is a logical workflow. Okay, and so this is something we'll come back to. But really, the idea is you say, I have this data frame. I want to work on this part of the data frame, and I want to do this to it. And this can be a bit more logical than some of the other ways that functions typically work in base. What's the vars for? So this is telling it's extracting out the information here from the entree column.
So the main thing that just happened was you converted that particular column into a character type rather than an integer.
Yeah.
Okay.
Yeah, that's the main thing that happened. And Yeah, so the vars section of it is just ensuring that you're not just dealing with the column as a tibble, I believe. Let me just double check. Could we have used untidy counts $ entree instead? Yeah, I believe so. That should have still worked. Yeah, so vars is used to basically saying, I want to select this variable. But you could have easily shortcutted it and used untidy counts $ entree, and that should still work. Okay. And so most things you'll find, as I mentioned earlier as well, tibbles most of the time will work with a lot of base tools. And so it's not like when you start using these things, everything's going to break down and everything you've learned already is not going to work anymore. That said, there are sometimes you'll find the odd tool that it doesn't work for, but it's very easy to just go back and you can just use the function that we met before, as.dataframe, and it will just convert what we have back into a data frame. So here we're just doing as.dataframe. Okay. And I'm just doing the head of that. And we're doing this with a pipe, which I'll explain in a little bit. But basically, we're passing this information into the head argument. So we can just see the first 12 rows. Okay, so it's super easy to go as tibble to get to a tibble and as.dataframe to get back. But most of the time, when you go to a tibble, you won't have to come back. And so I'm going to show you quickly how to make your own tibble. It's going to involve some steps that have some bioinformatic aspects to them and use some packages that will be introduced next week. And so the content isn't super important. It's more about the process of actually making the tibble. But what I'm going to do initially is show you some code just to get some data. Okay. And so I wanted to get some data that's related to these count information that we have here. Okay. And so when we have count information and we have some entree IDs, some useful things might be able to get would be to get some like positions, how long are the genes, or some symbols. Okay, and so there are some packages that exist in Bioconductor that are basically databases that contain that information. So this is for Homo sapien, so humans. And so we could load this in. We have the transcript database and just the organism database. And if I use the genes function on this, I'll get a bunch of information about the genes. Okay. And then if I use the, this is from this, I can grab the gene ID. And I'll use that to look up the symbol in this database. Okay, so I don't really need you to understand this code that much, and I'll show you the product in a sec. But you can hopefully see in a couple of easy steps, we've got a bunch of gene information from humans. And so I'm going to stick this together now and make my own tibble. So you do that with the tibble function. And it works much in the same way as the data frame function. Okay, so I want to create a column that's called ID, and it has the entree ID in it. Okay. And so I'm getting this from the symbols data frame. Okay. I'm also now getting the symbol. And this is also coming from the symbols data frame. And then I want to get the length. And we're getting that from up here. And so this, I'm getting the lengths of all the genes. Okay, and so what I've created here is a tibble that contains the ID, the symbol, and the length of every single gene in the human genome in this database. So you can see that it has 23,000 rows, it has 3 columns. And all we did to create it, right, was the same as we do with the data frame. We do tibble, we specify what the column names are, and then we put some data in there. So making a tibble is just as straightforward as making a data frame. That's really the takeaway from this. And we'll introduce you to these tools soon. But hopefully this gives you a taste of how quickly and easily you can start to grab annotation information. Okay. So tidying up the data. We have to figure out what is wrong with the count data frame from a tidy viewpoint. Okay, so we have these, this is our untidy counts. If we remember the rules, each variable has its own column, each observation has its own row, and each value has its own cell. And so I don't have a poll for this, but I'm going to ask if anyone could write in chat, or they can say it out loud if they have any ideas what could be wrong with this from a tidy standpoint. I'm going to pour myself some water when I do this. I think a key thing here is each observation has to have its own row.
So like we're missing 352 or?
No, but I guess so. This might require a little bit of abstract thinking, and I think Cart is almost there. So she's saying there's replicates in 2 columns. Yeah. Okay, and so that means you have replicate 1 versus replicate 2, and really they are separate observations. Okay, and really in reality, all of these are separate observations, and they aren't variables in themselves because they're things in your experiment.
So you would need to label it like 350_1 and 350_2, or?
Yes, kind of like that. Okay, so I should give you a show with this. So each observation should be a single variable with multiple columns. So I'll show you this in action. What we need to do is actually spin this round and have, for each gene, we have CD34.1, ortho1, CD34.2, ortho2. And then you can have the count for each of those as an observation. And so if this is not super clear, it will become clear in a sec. But to be able to do this, what we need to be able to do is to essentially pivot some of the data within itself. And to do that, we can use the functions pivot longer or pivot wider. So whenever you have content in a tibble, but it's not quite the right orientation, these tools enable you to rotate the data within itself. Okay, so if it hasn't been clear what we're aiming for, this is what we're aiming for down here. Okay, And so although this is actually maybe harder for you to necessarily look at, you don't get this nice clear gene, and then you look at the counts across. This is much easier for you to work with in a computational way. And so to be able to do this transformation, you use a function called pivot longer. And you may have heard of this in the context, there's another function called gather, which this recently replaced. And so if you ever figuring out how to do this, you might find information about gather. But it's more or less the same functionality. It's just pivot longer is slightly better and newer and being more actively developed. And so what it's doing is allowing you to collapse something that would be a single variable that's spread over multiple columns back down into a single column. And so this variable is, what sample is it? Okay. And so in this case, in the original case, the variable of what sample is spread over 4 columns. And so to get out of this, what you need to do is provide where you want the names of the columns to go. What do you want to call this new column? And where you want the values that were contained in those columns to go, and what should be the name of that variable. And so here we want the names to be called sample, and we want the count information to be go under counts. And so you can see this is all in the pivot longer. We have the data frame, we have names to, we have the values to. And then the last thing is, what column should we consider for this kind of compression? And so we wanted to consider everything apart from the entree. Okay, so it might be that you have a very long data frame and it's actually only 4 of the columns that you want to do this to. And so you can just directly specify which those 4 columns are. I'm lazy, so I said I did entree, but I did a minus. So that means everything but entree. And so now when it does this pivoting, it will consider the whole data frame apart from entree as fair game to be able to then do this compaction and this gathering of the information into a single variable. And you might find that you do this and you don't like it, or it may be you want to be able to give data to someone and you want to put it back the way it was because it's maybe easier for them to read if they're just going to look at it in Excel. And so it's really easy to go back. So you use a function called pivot wider. So there's pivot longer, which makes your data frame longer, and pivot wider, which makes it wider. And it used very similar nomenclature. So instead of going for names to, right, and values to, you instead say names from. And so you're saying, I want to get my names from the sample column and I want to get my values from the counts. Okay. And so this enables you to go back to the original data frame. Okay, so we've got something that is slightly tidier. The question is, what do we do next? Because this isn't quite tidy yet. And so we're aiming for each variable has its own column, each observation has its own row, and each value has its own cell. And so the thing we're missing here is each variable having its own column. And so this actually gets at what Cart was saying. Okay, so what you'll hopefully be able to see is that within the sample information, we have both information about what the cell type is, but also what the replica is. And so this is quite a common thing to see within your data. You'll be merging information. But actually you might want this separate so you can actually analyze the differences between what's replicate 1 doing versus replicate 2. And though you can do that already here within tissues, you might want to be able to do it across tissues because they are independent variables. Okay, and so a common function to be able to use is a function called separate. And so this allows you to split on like a regular expression into several columns. And so we'll show you how that works. So here's the separate function. We give it the data frame. We say what column we're interested in, right? And then we give it information about the separation. So we say we're interested in separating on an underscore. And we want to create 2 new columns, cell type and rep. And then we're also going to add this extra argument called remove equals true. And so that's going to remove the previous ID. So it's going to remove this, and we're going to create these 2. And you can easily switch this to remove equals false. If you want to have a specific ID for, say, a sample, you can keep it. And now you have 3 variables, 1 for the sample ID, but now you can also directly identify which is each cell type and which is each rep. So at this point, you pretty much have all the variables you can from your data, and it's organized in a very easy way to interpret. Okay, so that is what we're going to cover with tidying a data set. I'm now going to show you a bunch of tools for making use of this tidy data set. And I think the most important tool that I've learned to use, maybe that's overstaying, this tool of piping really enables you to start formatting your code in a much easier way to understand and interpret. And it makes it much easier to write code. Okay, and so what do I mean by piping? So when we often get when we're starting out, we write code, and it can be really easy to get like unwieldy with the amount of code you're writing. Okay, I just got a quick question about what we were doing. Could you still pivot wider after separation into replicates? You could. So you could separate this out into replicates, and if you remember the nomenclature for pivoting wider is this. So you can just say we're getting our names from this and your values from this. Actually, oh no, that might break it. Yeah, I'm not actually sure that would work. So yeah, where are we? So we have it here. If we pivot back wider after the separation, it'll be using this data frame, and we pick sample as the headers, and then you'd have counts along the bottom. You wouldn't necessarily, cell type or rep wouldn't have anywhere to go. So you have to, you wouldn't have any way to handle this. I don't think. I'm not sure what it would try to do. Sorry, my phone's ringing. I'll just turn that off. Yeah, because the so what will happen, right? With the nice way, reason why we're able to do that in the past is because each of these numbers is consistent when we go back. So 350, 350, 350, 350. And so when you pivot it back, it will collapse this down all into the same value because it's equal. But in this case, when you pivot this back, you'll have 4 different values here, CD34 through to ortho and 1 through to 2. And so it won't be able to collapse it down to a single value. Okay, can I explain the argument call? Yeah, I can explain the argument call. So, okay, so when you're pivoting longer, you want to, let's have a look at our original data frame. Here we go. So we have this data frame. We basically want the pivot longer action to work on these 4 columns, right? And we obviously want to keep entree, but we don't want that to be collapsed in any way with everything else. So we want pivot longer to work specifically on these 4 columns. So what the calls argument is doing is saying, these are the part of the data frame that I care about pivoting. And specifically, I could have written out a vector here, a character vector that says CD34_1, CD34_2, etc. as the names of the 4 columns. Or if you're lazy, you can, like me, you can just say minus entree, because what this is doing is saying, I want to do every column apart from the entree column.
Sorry,
Okay.
so does that, does that mean that you're basically designating entree as sort of the organization factor for your Tibble?
Yes,
like
yes.
You have to designate one of the columns for how you want to sort the data, and you said it was.
You can imagine a case where you also have several columns, right, that are not the pivoting. So you could have entree, you could also have the symbol, you could also have the chromosome you can find it on. And in that case, you don't want to pivot those either. And so in that case, you would also include that in what you're excluding. So the information going in here into calls is basically what columns do I want to collapse down into a single variable. And so in this case, I'm just saying everything but entree. But depending on your data frame, you might find that it'll be something slightly different. Cool. I hope that makes sense now. Great. Okay, so piping with Migrita. Okay, so what piping is it allows you to pass the result of one thing directly into another thing. And so what you might find is you build a code like this, and it can get very complicated very quickly. And earlier on, I talked about nested code. Okay, and so here we have a function separate, and then we have the function pivot longer, and they're on top of each other, and it looks horrible. And with so many arguments for some of these more complicated functions, it can get quite difficult to understand what's going on. And so I think the first step that people do to try and deal with this is they'll separate everything into individual lines of code. Okay, so we do the pivot longer operation, then we do the separate operation. Which is also, that works fine, but now we're saving intermediates at each step, and it's not super efficient. And so what we can do is use piping, and this allows you to pass a data frame into a function, and then the first aspect of that function will be used as the data frame. Okay, so I think it will be clearer once this is in action, but basically this is it's allowing you to take the output of one thing and then pipe it into the next thing. And this is without saving anything as a variable. And so then the thing that's nice about this is it actually helps you show kind of your logical flow as you go. Yeah, and so some of this is overwritten here. So I'm sorry, it's not super clear, but so in the boxes, it says pipe object takes object and puts it into the function. And then you can put in here which variable or observations do you want to work on. And so by using this, there's no intermediates and there's no, it makes the steps super clear. So it makes your it much easier to read than say like this nested code. Okay, and I think, so what's happened to here is the slide hasn't separated properly. So I'm going to quickly show you this, but I'm going to show you it on our single page format because the slide braked. Okay, so let me just find where we are. Okay, so this is what it says. So for those of you who haven't looked at our single page options, this is the single page has exactly the same information as our slides. It's just in a slightly different format. And this is the section that's not rendering properly. Okay, so what we're doing here, I'll fix this in the break. For those of you who are going to revisit this. But here is the code in action. So what we're doing is we have our untidy counts. We put it into a pipe, and then it goes into the function gather. Okay, this is the same as pivot longer, basically. And when you'd run gather by itself, you'd have untidy counts here as the first argument. And then once we've gathered, we can then run separate. And what this is doing now is it's passing the product of gather straight into separate. So it's doing all the steps that we just did in 2 lines, but it's doing it without saving an intermediate. So if you remember, we made something called tidy accounts. It's not saving that. And so the reason I like doing stuff like this is you start off by saying, oh, I have my untidy counts. I'm now going to gather them together using these arguments. And then I'm going to separate this out using these arguments. And then I have a product. Yeah, and so gather is the same as pivot longer. I obviously didn't update this piece of code, and I think that's why it's not rendering properly. So that is, I apologize for that. But basically, the pivot longer is basically this. Yeah, so this makes it like nice because you can then step by step add things as well. So how I often work with this is I will do untidy counts and I'll do gather, and then I'll add this and I'll do another line of code and I'll look at the output, and then I'll add another pipe, and then I'll add another line of code. And so I can iteratively run the same piece of code, but just make it longer and work through my problem without having to save all these different intermediates. And I think with it being relatively clear what I'm doing at each step. And so for more advanced piping, you can use a period as a placeholder to represent the object being piped in. So in this case, we have our tidy accounts. We then want to use tidy accounts. Okay. And we're going to use tidy accounts in two places here because we're using the period. And first, we're going to take tidy accounts. We're going to take the counts object. We're going to say what is greater than 0 to get logical. And then we're going to use that to index itself. Okay, and so this is a kind of a dummy example that it's not actually simplifying things, but you'll find as you start to pipe things together, you might want to be able to pull out specifically the input to the pipe. And then the last part about piping that we'll do is Magritta. So the pipe is part of the Magritta package, but it's also imported as a default by the Tidyverse. But the Magritta package itself also has some extra pipe options. And so if you load in Magritta, you will get access to this pipe, which I use quite a lot. It's a modification of the pipe, and it's considered to be a two-way pipe. And so once the expression is resolved, it will then assign the result back to itself. So in this case, we're doing exactly the same expression here. We're filtering by having counts of at least 0. So we're removing anything that's less, that's a 0. So anything without counts. And then we're assigning it back to itself. So tidy accounts at this point, yeah. So the question by Cart is, it overwrites the original object? Yes. So this is the whole point of this one, is it saves you having to do an assignment out if you're going to be updating the original object anyway. And you could have a long, like as long as you have this at the beginning, you could have a very long pipe. So this could have many, many steps. It could be something like this, right, with many steps. But if the first one is the double-sided pipe, then untidy counts would still get updated because it's evaluating all of the expression underneath and then assigning it back. Yeah, so that is the pipe. And so we'll start using pipes. I'll show you using pipes as we go through. But the big thing is to keep your eyes out. Base R doesn't have a pipe, but it's in active development. So you might start to see in the news, the R news world, if any of you start following R on places like Twitter, people are very excited about this at the moment. And so this will come out in a future R release. And so you'll be able to do this piping activity without having to use a specialist package. Although I'm sure a lot of people will just keep using this as well. Okay. Right, so we're going to get onto joining. I'm just going to get some more water. Okay, so in our first day, we talked about merge. And merge works really well to join different data frames together. But Tidyverse has its own way of doing things, and arguably it's easier to use because it has a whole range of functions depending on what you want to do with your merge. Okay, and so the key thing when you have these two data frames that you want to put together, it has some common key. And so in this case, we can use entree ID. So if you remember, we created a metadata column or a table, and we have our counts table. So we have our counts, we have entree ID, we have some sample information and counts, but then we also created this metadata table. Okay, and so that also has an ID. And so this ID and entree ID are the same, but they're not in the same order, and they don't have the same name. But what we can do is we can use a function called inner join. We say we want tidy counts, we want counts data, and you give it the information you want it to be linked together by. And so you said by, you do combine. And this is kind of interesting formatting here. You include both of the column names that you want to be joined together, and you separate them with an equal sign. And so when you do this, it joins everything together. Okay, I thought I showed you the data frame. I don't. It joins everything together, and it keeps only the objects that are have a match. Okay, so in this case, it will keep only the data objects that have a match in this original object. Okay, and that will become clearer in a sec when I show you some of the other joins. So there's a bunch of different ways of joining. Inner join keeps, like I was saying, keeps all observations in X and Y that have matching keys. So in this case, we only have some of the entree IDs because we only have 400 rows. Well, this is 24,000 or 23,000. And so these two will be linked together. We'll also have 2 extra columns for symbol and length here from this. And we'll only keep the ones in which we have an entree ID in this object. Okay, so wherever there's matches, we'll keep that, and that will be in the final product. There's also some other kinds of joins called an outer join. So a left join means you keep all the observations in X and those in Y with a matching key. So yeah, I'll show you some examples in a sec. A right join keeps all observations in Y while keeping all those in X with matching keys. And a full join keeps all observations in both. Okay, so here we have a left join. So we have our tidy counts, we have the metadata. It's exactly the same input. And you can see this would essentially have a very similar role to the inner join because of the way our data frames are organized. But you can see we only have 390 rows, we have our symbol, and we have our length. Okay, so this is a really nice way of merging data frames together. You can have our right join. Okay, and so if we remember with right join, this means that anything that isn't a match is also kept. And so I can have a look here at the tail of this object. Okay, so this shows me the bottom of the object. And you can see there's a bunch of things where we have the entree ID, we have the symbol and length, but we have no sample information, we have no cell type information, and we have no count information. Okay, so it just fills in the gaps with NA. Okay, so those are the common types of joins. There's also some filtering joins. So a semi-join is you keep all the observations in X that are matched in Y, but you don't include Y. An anti-join keeps all the observations in X that are not matched, and you also don't keep Y. Okay, so these are just ways of filtering your data. And so you can see again this in action. And so in this case, we're doing a semi-join. We're filtering down the counts metadata using the tidy counts. Okay, and so if you remember, this was 23,000 long. It's now only like 100. Or we can do the anti-join, and that only keeps the observation. We basically filter out all the results that have a match in our other data frame. Okay, so I'm going to stop right here and give you a poll about tidy data. I hope this joining and everything makes sense. as with the poll that we've done before, if you just, there's multiple choice and you can click on what's true and what you think is false. So we'll do another 30 seconds just to give people a chance to answer the questions. Okay, let's have a look at the results. So I think everyone did really good on the full join. I guess we did just cover that, so that's good. So let's dig into some of the answers for the other ones. So just under half of you said that you can use the double square brackets to get Tibble columns. Okay, so I guess again, my question design could be better, because you can use the square brackets to get Tibble columns, but what you get out is a vector. Okay, so a single square brackets, if you remember, is how you get a Tibble column as a Tibble, and a double square brackets gets you the Tibble columns as a vector. I think one person fell up on this, but Tibbles are not like matrices. They can accept a whole multitude of data types, and we saw that in action. And then pipes. So pipes allow you to loop over data. So pipes do not allow you to loop over data. What pipes do is allow you to stitch together your analysis and push one piece of data or one result into the next line of code without you having to pause, without you having to stop and save an intermediate. And one of the things that I want to highlight with this is, especially when you get later on into data analysis, that if you have an R session and you're saving every single intermediate as you go, this can start to really eat up your memory. And so by having these stitching things together like this, it saves you a bunch of storage memory, because you're not having to save all these intermediates. Apart from the fact that it can be easier to read as well. Okay, so I broadly think everyone did a good job there. Does anyone have any questions about anything we've covered so far? I know we kind of sped up a little bit towards the end because I'm waffling too much. But I think what I'm trying to highlight is you can do a lot of the same things that you can do in Base, but some of these tools are maybe better considered and have slightly better functionality. But they are both compatible. And there is this kind of ethos with Tidy that initially, when it takes a little while to click, but once you start using this with, say, ggplot at the end, it starts to make a lot more sense. So specifically with this data frame, right? Reorienting it to pivot wider and pivot longer, on a human readable level, it makes it in some ways harder to understand, because you're now spreading the information. You can't see in CD34.1, CD430 to 4.2, you can't see them side by side. However, when you put this into ggplot, it handles it a lot better, and it makes it much easier to draw plots with this information. Okay, so now we're going to go into a bunch of tools for quickly manipulating the data. And I think this is the suite of tools which really I use all the time, and I think is the most useful thing about today, apart from piping. And so this is all contained within a package called dplyr. And so the way that dplyr works is you have your function of choice, you give it a data frame, or you pipe in a data frame, and then you give it some parameters. And what it will do is it will manipulate the data frame to either filter it or subset it in some way or rearrange it. And it does it in a very intuitive way. And so the first function that I want you to learn is select. Okay, so this is dplyr select. And so we have our data frame here, our tidy counts meta. We can just use the select to grab one of the columns called counts. Okay, and so you might be saying, oh, I could just use indexing for this, right? And you could, but select has more operations to it. So you could also select from multiple columns. So here we do select, counts, and entree. And the really nice thing about this is I find this much easier to understand than indexing, because you're like, I want to use the function select on this data frame, and I want to get these columns. You can also use the negative to exclude a variable, or you can use a range. So you're still using the names of the columns here, but you can use a colon like you would a number. And so it's similar to saying like 1 through 5 or whichever this is. So yeah, it would be something like 2 through 4 or something. Okay. And so that's the way select works. Select is focused on your columns. It enables you to quickly grab different columns that you need. Will a minus range work? Okay, so you want to remove a group. I'm not sure. I haven't tried that. So there's a question from King. He was asking, will a minus range work? I could give that a quick go. If anyone has, I don't actually have any of the data loaded in right now, but I can quickly load some of them in. And so I'm going to quickly switch over to my RStudio window so you can see. I'm going to load in. Let's do my tidy data. What do we have? Let's have a look at tidy counts expressed. Yeah, this will do. So we'll do tidy counts expressed. And I need to get dplyr in here. So I'm just going to do this. And we're going to do select. And then we want to do a range. So let's look at the col names. Or we could just do head. Oh, let's do this. Okay, and let's make this bigger. Okay, so we have a group of columns. So I could still use cell type to rep. Let's do that. So we're hoping here that this will remove cell type and rep. and doesn't get upset. Okay, but that didn't work. It did remove something. It removed counts and counts total. Maybe I need to throw this also in some parentheses. There you go. So you can do it, but you just need to make sure that whatever you're using your minus sign on is surrounded in parentheses, so it knows where the beginning and end is. Cool. So it's quite flexible, it seems. Okay, so that's working with columns. Okay, so now we're going to switch over to working with rows. And this is, select is fine. I can make an argument that it's slightly more intuitive than using indexing, but it's quite similar. The filtering, however, is really nice, I find. And so the way that filter works is it basically is looking for a logical. You provide it a logical, and it will filter all the rows based on that logical. So in this case, we're using filter, and we're saying we want to do it on this data frame. And we're saying sample is equivalent. So this is the double equal signs. CD for CD34.1. So what this does is it subsets all our data to only include the CD34.1 data set. I can also use the in operator, which we met before. So you can say sample in this, and we filter this. Okay, so we met this one before. It's just going to be a true or false based on which of the samples, which of your sample is contained within here. Okay. And so again, what I haven't spelt out, but you may have noticed is when you're doing this, you don't actually have to directly say, I want to look in tidy counts meta sample. As long as it knows you're working in the tidy counts meta data frame, the sample name, it can infer that that is from here. So you don't have to spell out this also in the second part of the argument as well. It knows what columns are available to it. We can use numerical operators. So in this one, we're asking counts greater than 0. So we kind of did a little bit of that earlier on as well. And so we're saying we want to filter counts greater than 0, and we'll filter based on that. Okay, so that's filter. Filter is relatively straightforward to use, just like select. They are their each equivalents, but with filter, you need to provide a true false. While select, you're saying, I want this column. And you have to specify which column. We'll also use a range a lot. So a range is a nice way of arranging based on, say, a numerical order. And so here we're saying, I want to arrange by my counts. Okay, and it will make it in ascending order. So this is actually one of the things you'll find is everything is done in an ascending way first. And most of the time when I'm looking at something, I want to know what has the most counts. And so you have to reverse it. And so in this case, we can just say, I want to do descending. So you put the descending function around the counts, and it will change it to descending. And then we can see which genes have the most expression. Okay, so you can see we're using all these different functions, and they have exactly the same format for them. Okay. So this is the strength of the tidy packages. Okay, and so one of the functions we met earlier was mutate. And so mutate is used for creating a new variable. And so you might want to do some form of computation and then add this column on at the end. And so in this case, we're going to use the scale function to create a z-score of the counts. Okay, and so the way we do this is we just say mutate. Again, we're just telling it what our data frame is. And then we say we want to scale the counts. Now, at the end, all the z-scores are added. And to make this even nicer, you just have to, if you want to specify what the column is called, you just add in the name prior to the actual computation. And so you create a named variable in a super, super easy way. Oh, so we have a question from Adam. The counts are red in my output except for 7.19. Is that because they are within 1? I think that is
could be just because they're negative. I've been getting like null values showing up as red or sometimes 0.
yeah, exactly. So I can't each data type has different color coding. I can't remember. It depends on what data type you have it read in as. I can't remember what each one corresponds to, but the color coding is just another level in which Tibble tries to help you make the Tibble more readable. It's not a bad thing or anything like that. It's a formatting thing to make it more legible. But I cannot remember the exact rules off the top of my head. I also just got a message from Cart, she's played around with Tidyverse a little bit as well. So she's suggesting that you can use the add underscore column. Okay, so why don't we give that a go? So I haven't used the add column before. So we're at the moment using this. And so we'll do this. Okay, I'm going to just switch you over to my screen. Okay, so this is what we're doing. We're taking, I have a slightly different data frame, but we're doing very similar things. So we're taking our tidy counts and we're adding a scale, right? And yeah, and so now you can see this, this negative coloring in red. And so Cart is suggesting the add column function, which is a Tibble function. And so with add column, we would do much the same thing, I believe. Never used it before, but let's see if this works. Let me have a look at this. Help. Okay. I'm not sure if I'm going to be able to make this work on the fly. But something I've noticed here in the observations. Okay, so one of the nice things about mutate. Okay, I'm not saying that add column is bad or not a great thing to do, and I'm going to have a little read into it to see if we can add that to the course. But the nice thing about mutate is, say I wanted to modify an existing thing. So we have our counts, and I wanted the counts to actually now represent the scale of counts. When I do this, the counts are now updated. So what this means is you can overwrite an existing count, an existing column with the mutate. So if you want to dynamically update your data set, then you can do that. With add column, it seems that that isn't possible. However, it might be easier to do other things with it. So yeah, we're getting a suggestion from Doug that maybe we could do, we'd have to use the $ itself. So we can do $. Oh, there you go. Okay, so with this package, you might actually have to specify where it's coming from. So here I'm actually specifying that I'm using the dot. So this means I'm specifying that I'm getting the data from this data frame. I'm using the $ to grab out the counts, and then that all gets added onto the column. So yeah, this feeds into this idea that there's many, many different ways to do everything. Okay.
Yeah, and I was just going to say, it looks like add column maybe can also add columns within the, it doesn't automatically, I mean, it doesn't have to add them at the end of the table.
Oh yeah, so that's if you have a specific data frame in mind and you like a specific organization, that is quite nice to do, because with mutate, you'll add them at the end unless you overwrite something, and then you'll have to use select to then reorganize everything. So you can use select or indexing, whichever you prefer, to not subset your data, but just to put tail select to do the order that you want it to do. But that is multiple steps, and if you can do it with add column in one step, that's really nice. Okay, so summarize is the next function we're going to talk about. Summarize is a really nice way of applying some aggregating or summary function to a group. So a big example of this, if you want to count all the how many times you see a certain group, this is a good one to use. So first, what we're going to do to have a good data frame to trial this out with is we're going to subset our data set to only those that have a count of 0. Okay, so this is our table with 0 counts. And then we can, when we want to summarize, we have to tell it grouping information first. Okay, so when we want to do any kind of summarization, you need something to summarize over. And so first you use the group by function. So in this case, I really want to know the answer to how many 0 counts do I have in each sample. Okay, so to get at that, I'm going to first isolate all the ones that have 0 counts, and then I'm going to say group by that sample. And then I can use summarize. And if you ever want to do summarize and get a count, you can use the function n parentheses. Okay, so this is a counting function. And as a result, I now have a number of how many genes in each sample had 0 counts associated with it. And so you can see here it's tissue specific, but there's also some variability between samples. Okay, so whenever you do a summarize, any kind of summarization, you have to, there's 2 steps. You first group your data and then you summarize. Okay, and you can see we're tying everything together here with the pipes. And so the n for counting is one kind of example of a function that you can use in the summarize, but you can use a whole bunch of different statistical things to just get some information about your data between the groups. So in this case, what I'm going to do is I'm going to take this in, and then I'm going to group by entree. So this means I'm grouping by gene. And then I'm going to get the mean of the counts. So this means I'm able to get the mean gene counts across all of my samples. Okay. And so you can see the output here. We have the counts mean. The other thing we're doing here is we're actually assigning the name of the column as well. So you can do that in Summarize. So this is a common way of whenever you're creating a new thing in your tibble, you can just add an equal sign before and give it the name that you want as your output. Okay. So Summarize is super powerful and very useful. You can also take this a step further and actually group by several things, and there's a hierarchy in the grouping. So in this case, I actually don't care about the average count per gene. I care about the average count per gene per cell type. Okay, and so that's the whole point of having replicates, right? You can have redundancy and stuff like that. And so what we do here is in the group by, we just say, I really care about gene, but it's gene by cell type. And so when we do this, it's exactly the same. So we're going tidy counts into the group by, into the Summarize. We're getting our mean counts. And you can see this was definitely important to do because there's quite a lot of variation between cell types. And so that's showing you an idea of how summarizing works, but grouping is not just limited to summarization. And so in this case, we can, anytime you group, any operation you apply to it, if appropriate, will be done in its groups. And so that can also apply for filtering. So in this case, I'm taking my tidy counts, I'm grouping by sample, and then I'm ordering my counts. Okay. And I'm ordering my counts to be decreasing. So this means I'm ordering my counts. I'm ordering my counts from most expressed to less expressed. And I want to find out the top 3. So I'm saying which of my counts are in the top 3. But because I have grouped this by sample, it's going to be doing this on a per sample basis. So that means you'll be able to find out what are my top 3 expressed genes in each of my samples. And so you can see the product of this when we put it into filter here. So we have each of the samples and we have the highest expressed genes in each of these 3 samples. So this didn't work very well at all. Cool. And so as you stitch this together, you can start to do much more complicated complicated interrogations to your data and much more complicated filtering or things subsetting of your data to have a look at what's going on. And so in this case, we're filtering instead by not counts that equal 0, but counts that do not equal 0. And so if we remember, this has been stylized, but the way we would do this is we would do an exclamation mark and then an equals to get does not equal. Then we pass this into cell type and entree. So we're grouping by gene, we're grouping by what cell type it is, and then what gene it is. And then I can filter based on the counts that you have of each. And so what this is doing is saying, I only want to focus on genes that don't have 0 counts. And if in any case, when I've filtered this down and I count them up, there's only one observation that's past this threshold, that means the other one had 0 counts. And so we can filter those out. Okay, and so I don't know if I explained that very well, but the aim of this is to filter out, the aim of this code is to filter out any examples where we have expression of the gene, but only in 1 or 0 of our samples, okay? Per cell type. Okay, so in a case where you have CD34_1, you have some count values, but then in CD34_2, you had 0 count values. And so you might want to filter those samples out. Okay, and so what we do in the first step is we filter it down so that anytime there's a 0 value, it's filtered out. And so that means every entry with no counts is gone. And so in our example where you have 1 expressed and one not, the one that is not expressed is gone. Then we do our grouping, and then we count in these groups. So any example where there was 1 that wasn't expressed, that has been removed, and when you count now up how many there are, it would be 1 or 0. And anything with 2, because we have 2 replicates, would mean there's counts in both of them. Okay, so if that doesn't make sense, I'm sorry I didn't explain it better, but the best thing to do is work with this code, look at it in step by step, and try and get to grips with how the data is being transformed at each step. And so that's really easy to do with this piping, right? Because you can just start at the beginning, and then you just add each pipe back. Okay, could you explain how grouping around two variables changes it? Yeah, so give me a sec. So whenever you're grouping by 2 variables, it just means if you have in this case, we have like CD34 and I forget, ortho, right? And so we can group by cell type, and we'll have 2 groups, ortho and CD34. If you group by cell type and rep, you'll have ortho and 1, ortho and 2, CD34 and 1, CD34 and 2. And so now you have 4 groups. And so it's just about combining, when you group by both of these things, it will find every individual instance where you can combine these 2 groups, and they would then be their own group. So it allows you to just kind of subset your data on multiple levels. So I think that example is the best one. If you just grouped by one thing, it would divide your data into 2. If you grouped by cell type, you'd have CD34 and ortho. Or if you just grouped by rep, you'd have 1 and you'd have 2. But if you group by both at the same time, then it would divide it up into the 4 groups. Okay, we already have samples, so that's maybe not the most useful thing to do, because sample, if you grouped by sample, it would do the same thing. But you can also imagine the case where you do it like we have by cell type and gene ID. And that means you now have a group for every single gene in that cell type. And so that means you can compare the gene in that cell type versus the gene in the other cell type. And it's grouping together. What's being grouped together is the replicate information, because you have, that's the difference between the 2 observations you'd have. Cool. So that is grouping. And so just to kind of finish off with dplyr, the piping can become really, really useful, because what we covered yesterday with ggplot, you can just take all this information and just keep piping, and then just put it straight into ggplot. Okay, so in this case, we are getting the mean, we're doing groups in much the same way I just explained. We're doing by gene, but also by cell type. We're doing the mean counts of these. So this is getting the basically the means between our replicates. because we're considering this, grouping it by cell type and entree. Okay, and so that once we group that, we should have for each group, there'll be 2 entries, and these will be replicate 1 and replicate 2. And once we get the mean, we can then we can pivot this wider. Okay, so we want to get the names from the cell type and the values from counts mean. And then we can tuck this into a ggplot. And it'll look like this. Oh, it's kind of hidden. But it'll go straight into, you can go straight into ggplot. I need to alter the size of this so it fits. Okay, so here we're just making a simple XY plot. And so you can use your pipes with anything. You can use them with base. You don't have to just use them with Tidyverse. I use them for all the code that I write. It's just important to remember that whatever you're passing in is going to be used by default as the first argument in your function that you're passing it into. And so if that's not the case, you need to specify the argument names. Okay. So we're getting up against it with time. I'm thinking there's a last section about strings, which we might just not do today, but it's available for you to look through. I'll give you a quick 5-minute just rough idea of what it encompasses though. But we'll probably just finish with outputting your tidy data, I think. And so reading out again is just as simple as reading in, and very much as simple as base as well. There are specific functions, write dlim or write underscore dlim and write underscore CSV. The really big difference compared to base is it doesn't write out row names. And that's because, as I mentioned at the beginning, tables as a default do not have row names. Okay, it's generally discouraged because they are a variable in themselves. Generally, there's some kind of ID, and often they're useful in some regards. You might want to use some filtering based on those or something like that. And so you want to actually keep it in your active data frame. But yeah, and so once you have your tibble, it's super easy to just use these, because I don't think that using the regular write.csv, the base version, will work with the tibble. So you can just use this instead of converting it to a data frame. Okay, so this is the last section. It's strings, but yeah. Actually, I could go. There's 14. There's like 10 slides about it, so I could go through it pretty quickly. Yeah, I'll go through it quickly and give you a rough idea of what's going on, but I won't go into detail unless people want to stay and ask me questions afterwards. How about that? That's a compromise. That's what we're going to do. Okay, so string R is a whole set of it's a package, and it has all of the kind of string comprehension aspects of Tidyverse. And what I mean by string comprehension is when you have a character, and you might want to alter the character based on its properties, like what letters it has, if there's any patterns, anything like that. And so especially if something has something from data entry, there's often errors, and so you'll have to fix them. Maybe someone writes everything with capitals, and then someone else writes it all lowercase, that kind of thing. Or stuff like white space, that's another big one. So string R is a pretty comprehensive way of doing that. But there is a sister package called string I, which has even more stuff, but string R does the majority of what I need. Okay, and so this is what I mean by a string, right? So we have the names of the BRC team members, and Tom, who's our fearless leader, his name is a string, right? And we have these different strings within our vector here. And so there's a lot of different functions to be able to manipulate these. String sub is one of the easiest ones to get your head around. What string sub is doing is it's creating what's called a substring. So that means you're extracting out of the string. So here you say, I want to extract the first from the first value to the third value. Okay, and you can see it applies it to the whole vector, which is nice. It's vectorized. You'll find that some of the base functions that do similar things are not vectorized. And so they'll just do it on one string at a time. And then you have to wrap it in a for loop or an apply to actually get it to work. Well, this will just do it, no problems. Okay, you can also add minus values. And so that will count in from the end. You can also replace with string sub, much in the way that you would do it with indexing. And so in this case, we're replacing anywhere from 2 in to -2 with an x. So we just get the beginning and ending surrounding an x. You can also replace things. So, oh, this isn't working here because I already updated. Okay, I need to write a note of that. Sorry, so what's happened here is I've updated the string for BRC so that my name isn't there anymore. And then when I look, what we're doing here is we want to replace Matthew with Matt, because that's what I go by typically. But it doesn't exist anymore because the X is there. But for you guys, really, the string replace all function is just like a find and replace. And you can do this with anything. Again, this won't work very well, but you could do it with a U to a Z. You can use it with long strings, however you want to do it. And there's also methods to replace white space. So again, string replace all can help you replace white space. So here we just have a gap, and you have all these gaps up here. But quite often, actually, you might want to preserve white space that's within a string, like here, although you wouldn't want to preserve this. But you want to strip away the white space that's on the outside of the string. So there's string trim for that. Likewise, you might want to add white space so that all of your strings are exactly the same length. And so in this case, it's going to add space to the left-hand side until the string is a width of 10. Okay, and so then it dynamically updates or adds white space depending on the size of the string. You can also capitalize things and decapitalize things using the string to title, or string to lower also works quite well, string to upper as well. Okay, and so you can see how I'm using this to do it with gene names, because quite often you want to convert between a gene name and a protein name, or a human versus mouse. That isn't necessarily the best way to do it because not every single gene has a direct homologue that is like that, but it's a quick and easy way of doing it. And then we have string detect. So detect gives a true or false about whether a pattern is present. So this is similar to grep, if anyone is familiar with grep. And so in this case, I'm going to look for all the gap genes. Okay. And then I'm going to put that into a filter so that I can then subset my data frame to all the gap genes. Subset doesn't give a true or false like this one. This one gives a logical. This one actually just returns what the matches are. So you can actually look at what the gap genes are. And you can do things like count as well. So this will count how many times we see this within a given string. So all of these gap genes only have one version of gap, but maybe you're looking for something that's repeating. And so you can count how many times A appears or something like that. Okay, so that was my very quick going through strings. So not to keep you for too long, I want to not wear you out before we get to our Markdown and GitHub later this afternoon. So getting into Tidy beyond this, the Tidyverse pages are really comprehensive and they're really nice. They're very pretty websites, but they have lots of information about their packages. They're regularly updated blogs, and you can learn extra stuff there. He also wrote a paper about being tidy. So this is slightly different to his. Oh, this link's not working. Okay, I need to update this link. Oh, no, it is working. I just had the full stop. Okay, so he wrote an actual peer-reviewed paper about Tidyverse. So if you want to get into the science behind why it could be useful, there's that. There's a bunch of other packages that we're not having time to cover, but anyone handles any time data and they want to be able to like add a week or subtract a week, that kind of stuff. Lubridate is really good. And then there's some other links to some good resources for this kind of thing. Okay, so that is that. I will chuck up a poll because I love my polls to try and see how everyone feels about what we just covered in the last half. That said, we are overrunning, and we will restart at 1 o'clock. So I'm sure everyone wants a break. So if you dash, that's also good. And of course, if you have any questions, let me know. Okay, right, I might, oh, we've still got some people rolling in. I'll give it 20 more seconds. Okay, so let's have a look. I think most of you got this fairly straightforward. So we have a simple choice between filter and select, which one allows you to interact with rows. It's filter. Filter is all about rows. Select is all about columns. New variables are created with mutate. Yeah. But Car also suggested we can use add_column. They have slightly different nuances about how they work, but both of them are tidy ways of doing things. And then string R functions manipulate numerics. So we just went over that very, very quickly, but it's all about strings and characters. Okay, so character strings. And so they allow you to do all kinds of things to manipulate your strings. And they're super useful if you ever get into the business of having to clean up some metadata, anything related to clinical studies and stuff like that, or ecology studies where you're having to write stuff down from rather than just having numbers. They are super useful. Okay, and so with that, we're going to have a little break. We are back up at 1. So hopefully I'll see most of you there at 1 o'clock, and we're going to be talking about R Markdown. And so this and reproducible reports. So this is really important for the future of your coding, and it's really good practice to start to learn how to do this early on. Okay, and like I said, any questions, I'll be around, and I am going to stop the video and mute for now.